Alright, so we're looking at question number 5 from the 2016 exam. And it says, at high temperatures, the compound C4H6, which has a crazy organic name, 1,3-butadiene, but you don't need to know that, that's just its organic name. It's reacting according to the equation above. So two of those molecules collide and makes a C8H12. The rate of the reaction was studied at 625 Kelvin in a rigid reaction vessel. Volume's not changing. Two different trials, each with a different starting concentration, were carried out. The data were plotted in 3 different ways. So we're looking here where we just have concentration versus time. Trial 1 is this line, trial 2 are the squares. I've got time in seconds. I've got my starting concentrations. I started at 0.02 moles per liter for the first trial, 0.01 for the second trial. And then, of course, I manipulated the data, the axes, and I plotted the natural log concentration versus time and 1 over the concentration. So hopefully you're like, ding, 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 I see a straight line here, so that's going to be significant at some point. But the first question says, for trial 1, calculate the initial pressure in ATM in the vessel at 625 Kelvin. Assume that all the gas present is just the C4H6. So I look at my trial 1, again, just concentration versus time. Trial 1, I start with 0.02 moles per liter. So what you just do right now to make your life easier, you assume that that's 0.02 moles, and you've got 1 liter from your vessel. And now you've got moles, you've got 1 liter, you've got a temperature, Pivnert. Alright. So I'm looking for the pressure. I'm calling it a 1 liter vessel with 0.02 moles in it. It says calculate in atmospheres, so I want the 0.08206 value for R. And be careful, it's already in Kelvin, so don't add 273 to that. You're just using 625 Kelvin. And when I plug and chug, I get 1 atmosphere of pressure. 1.0 matches up with sig figs. That's good to go. Now part B, it says use the data plotted in the graphs to determine the order of the reaction with respect to C4H6. Now it shouldn't be a very big surprise because you need 2 of these molecules to collide. But looking at the data, I've got my straight line graphs with my 1 over the concentration, which is indeed reflective of my second order reaction. So 1 over the concentration versus time gave me my straight line. So that's how I determine my second order. Don't use the balanced equation. I was just showing it to you to say, well, it makes kind of sense. But when it says use the data plotted in the graphs, that's how I know it's second order. And so now it says the initial rate in trial 1 is 0.001 moles per liter seconds. So let's calculate the rate constant for the reaction at this temperature, because of course the reaction rate is temperature dependent. It doesn't say anything about appropriate units, so you don't have to worry about that here. It could, if there was a different question, but it doesn't say it here. But I need to, my rate law is K times the concentration of C4H6 squared. Alright, and so now I plug in my rate. As it says, the initial rate is 0.001, so that's over here for my rate. Where did the 0.02 moles per liter come from? Again, this is trial 1, and we started with 0.020 moles per liter. That was the concentration of my C4H6. That, of course, has to be squared because it's second order. So K is equal to 0.001 divided by 0.02 squared. I get 2.5. And again, it doesn't mention with proper units in the question, so if you just answered K equals 2.5, you got the point there. If they had said with appropriate units, a second order reaction would be liters per mole second, and that would be the appropriate unit. Alright, a nice little rate question there. Hope this helped, and I will see you soon.